Hello, everyone. This is a lecture on section 9.3 on the statements of Celo's theorems. So in this section, it's just a statement and some application of Celo's theorems, not the proof. That's in a later section, although I don't think we're going to get to that because we're running out of time, and there's one other topic I'd rather cover than proving Celo's theorems. But we can just go with the statements and talk about those. So recall Cauchy's theorem. If G is a finite group and P a prime such that P divides the order of G, then G has an element of order P. So that was Cauchy's theorem, and just a remark on Cauchy's theorem is the following. If G in G has order P, then H equal to the cyclic subgroup generated by G is a subgroup of G of order P, right? An element of order P gives you a subgroup of order P, the cyclic subgroup. So Cauchy's theorem is a simpler form of Celo's first theorem. So theorem 1, or theorem, this is Celo's first theorem, and it states the following. If G is a finite group and P a prime such that P to the K divides the order of G. So not the prime, but prime to some power. So like if G has order 20, then 4 divides the order of G. Right? Or if G has order 80, then 8 divides the order of G. 8 more, 16 divides the order of G. So on and so forth. Then G has a subgroup of order P to the K. All right, that subgroup need not be cyclic, but it's a subgroup of order P to the K. So that's Celo's first theorem. And and this is in contrast to that example of the converse of Lagrange's theorem, right? The group A4, the alternating group on 4 symbols, had order 12, but it had no subgroup of order 6. Right? 6 divides 12, but there was no subgroup of order 6 in that group A4 of order 12. Of course, 6 is not a power of a prime. 6 is 2 times 3. Celo's first theorem says that, if a prime power divides the order of a group, then you have a subgroup of order that prime power. All right. Definition. If P to the K divides the order of G and P to the K plus 1 does not divide the order of G, right? Then the subgroup, a subgroup H of, then a subgroup H of order equal to P to the K. So the subgroup guaranteed by Searlow's theorem. To exist by Searlow's first theorem. All right, is called a Searlow P subgroup. Of G. So, for example, what I mean is the following. So, for example, if the order of G is 80, right, then and 80 is equal to what? What's the prime decomposition of 80? It's 16 times 5, right? 2 to the 4th times 5. Then the Searlow 5 subgroups have order 5, and the Searlow 2 subgroups have order 2 to the 4th. So in a group of order 80, you have Searlow 2 subgroups, which have order 16, and Searlow 5 subgroups, which have order 5. Okay, now there's a close relationship between Searlow subgroups for the same prime, and this is given by Searlow's second theorem. If A and B are Searlow P subgroups of G, then there is little g in G such that G inverse is equal to B. So, right, as a set, right, where G inverse, I mean, we've covered this one before, but here, G inverse is equal to the set of all G inverse, such that A is in A. Okay. So again, this operation is called conjugation, and it's saying that any two Searlow subgroups are conjugate to each other. Okay, for any other orders of subgroups of G, that need not happen. But for those maximal subgroups of order P to the K, you have this conjugation property. And then Searlow's third theorem if M is the number of distinct Searlow P subgroups of G, then two things. One, M is congruent to 1 mod P, and 2, M divides the order of G. So two properties of the number of distinct CeLO P subgroups of G. Right? The number of subgroups is equal to 1 mod, is congruent to 1 mod P, and the number of subgroups divides the order of G. All right, so let's take an example. Let G be a group with the order of G equal to 115. 115, the prime decomposition is 5 times 23. Right? 5 is prime, 23 is prime. So pretty simple prime decomposition. Find all possibilities up to isomorphism for G. Okay, all right, well, let A be a CeLO 5 subgroup. Oh, I'm sorry, there's one other corollary to this. One other before the example. I apologize. Let me add a page here. All right, so a corollary of CeLO's second and third theorems is as follows. So a CeLO P subgroup H in G. A CeLO P subgroup H of G is a normal subgroup of G. If and only if, okay, the number of CeLO P subgroups of G is 1. So, CeLO's third theorem says that the number of distinct CeLO P subgroups of G is congruent to 1 mod P. Okay? Here, all I'm saying is that a CeLO P subgroup will be normal if and only if the number of CeLO P subgroups is 1. Proof, so we'll actually do the proof for this one. If H is a normal subgroup of G, so let H be a CeLO P subgroup of G, so in this direction, if H is a normal subgroup of G, then for any little g in G, right, CeLO's second theorem implies, if H is a normal subgroup of G, then for any g in G, HG is equal to GH, that is, H is equal to GHG inverse. All right, Silo's second theorem says that any other Silo P subgroup of G would be conjugate to H. However, H is equal to G, H, G inverse always, so there are no other Silo P subgroups. So there are no other Silo P subgroups because G inverse is equal to G for all G and G. So there are no other Silo P subgroups. Thus, the number of Silo P subgroups is 1. Coming back the other way, if there is only one Silo P subgroup of G, then you must have that subgroup H of G, then we must have that G inverse is equal to H for all H and H, or for all G and G, because the order of G inverse is equal to the order of H, and so G inverse is also a Silo P subgroup of G. All right, so a Silo P subgroup is defined simply by its order. You know, for groups of order 80, Silo 2 subgroups have order 16. So if this is a Silo 2 subgroup of order 16, this is also a subgroup of order 16, so it's a Silo 2 subgroup. But if there's only one Silo 2 subgroup, then it's going to be normal, because it's going to satisfy this for every G and G. Thus, GH is equal to HG for all G and G. So H is a normal subgroup of G. All right, so normality of Silo P subgroups is simply dependent upon the number of Silo P subgroups, and the number of Silo P subgroups is constrained. It's congruent to 1 mod P, and it has to divide the order of the group. So that puts a lot of restriction on things. Can put a lot of restriction on things. Cut and or paste. Here it is. So, for example, let G be a group of order 115, which is 5 times 23. Find all possibilities for G if the isomorphism. Let A be a Silo five subgroup of G. Okay, the number of Silo 5 subgroups in G could be, well, must be, congruent to 1 mod 5, and must divide 115. must divide 5 times 23. Well, actually, it has to divide 23, because 1 mod 5 never divides 5. All right. So it must divide 115. Well, it must divide 23, actually. So the number of CeeLo P subgroups, so the only possibilities are 1, 6, 11, 16, 21. That's it. Because any more than 21 is bigger than 23. Right? This is not a divisor of 23. 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 So that's the only possibility. So the CeeLo 5 subgroup is normal. Right? Let B be a CeeLo 23 subgroup of G. The number of CeeLo 23 subgroups of G is 1 mod 23 and divides 115, which is equal to 5 times 23. Well, if you're going to be 1 mod 23 and you're going to divide, well, you have to divide 5. Right? Because 1 mod 23 never divides 23. Right? So 1 mod 23 that divides 5 is only 1. The only possibility is 1. So B is a normal subgroup of G. Right? So A has order 5. Since order A is 5, A is isomorphic to Z5. Right? Since B has order 23, which is prime, B is isomorphic to Z23. Right? The order of A times B is, the order of A intersection B is a common divisor of 5 and 23, because it's a subgroup of A and B, right, which is 1. So A intersect B is just the identity element. Right. And the order of A times B is equal to the order of A times the order of B over the order of A intersection B. So that's 5 times 23 over 1 is 115. So the product of those two subgroups is all of G. Right? So we have that A and B are both normal subgroups of G. A intersection B is the identity, and AB is equal to G. So, G is isomorphic to A cross B. Right? That's the 3 conditions for a group to be isomorphic to a direct sum of subgroups. The subgroups are both normal. They intersect in just the identity. And their product is the whole group. By section 9.1, right? That was from 9.1. That's an important theorem. So G is isomorphic to A cross B, which is Z5 cross Z23. And since Z5 and Z25 and 23 are relatively prime, This is just Z115. So groups of order 115, you've only got this cyclic group. I got one more example I'd like to do in this section. We talked about groups of order 21 a long time ago. The classification was a little sloppy. But now with Celo's theorems, you can do it pretty simply. Okay, so we'll talk about groups of order 21 in part 2.